protozoa, the single-celled organisms, are the largest microbes living in the rumen. Perhaps more important, and certainly more numerous, are the millions of bacteria. Bacteria are so small and transparent as to be hardly visible under the light microscope unless specially stained, like these. Bacteria come in many shapes, some joined together in long chains. Many are rod-shaped. Some are spiral. So, bacteria and protozoa in the rumen break down the cellulose cell walls into simple substances that the cow can make use of. The microbes multiply rapidly in the warm rumen, and when they die, millions are absorbed by the cow. Beef not only comes from grass, but from microbes too. Meat contains protein, which is essential for our health. Now, cows get their protein from plants. But where do plants get their protein from? Consider the pea plant, for instance. This plant makes protein with the help of certain bacteria in its roots. On the roots are a number of swellings or nodules. If we look at a section through one of these nodules under an electron microscope, we can see that each cell contains hundreds of dark dots. Each dot is a bacterium. These bacteria convert nitrogen from the surrounding air into nitrate, a form of nitrogen in solution that the plant can use to make protein. Without nitrogen-fixing bacteria, there would not be enough nitrate in the soil to support a healthy crop. Many food plants don't have root nodules with these bacteria, and so artificial fertilizers are needed to provide these essential nitrates. As the cost of fertilizer continues to rise, scientists are looking for ways of making wider use of nitrogen-fixing bacteria. So, microbes play an important part in food production, in the field, and also in the factory. Cheers. In Britain, we drink more than 17 million litres of beer every day. Its production depends on a single-celled fungus called yeast. Yeast is used as a catalyst to convert the sugars extracted from barley into alcohol and carbon dioxide. The yeast multiplies rapidly and rises to the surface as a froth. This has to be skimmed off. What's underneath is beer. And to finish my meal, a nice piece of cheese. Cheese is made from milk and a special ingredient, microbes. Here, millions of bacteria are being poured in. Different microbes give the characteristic flavors to different cheeses. Much of the food we eat contains waste products like cellulose, which we can't make any use of because we can't digest them. Now, these have got to be got rid of. And the more of us there are, the bigger the disposal problem. The waste from homes and industry is carried through sewers to the sewage treatment works. The sewage flows into large tanks where the solid material has time to settle, and after a few hours, the clearer liquid flows from the top of the tanks to be treated by microbes. In these tanks, microbes are mixed in with the sewage. Warm air is pumped through the tanks,
This not only warms up the water, but provides a continuous supply of oxygen, an ideal environment for bacteria, which quickly multiply, feeding on the abundant supply of food. There are other kinds of microbes here too, particularly protozoa. They feed on bacteria as well as sewage. Some protozoa live in colonies. Each individual is attached by a stalk. They feed by beating their hair-like cilia, creating a current that carries food particles towards them. After 8 hours in the activated sludge tanks, the fluid is allowed to settle. The result, water clean enough and harmless enough to be discharged into the river. But what about all the heavy sludge that settled onto the tank floor? Well, it's pumped into large underground tanks. The contents are heated to about 32 degrees centigrade, and bacteria start to digest the organic material. After 3 weeks, the sludge is pumped to large open lagoons. Here it's left to dry out for about 5 years. At some sewage works, the sludge may be pumped into the sea. Here, it goes onto the land. This treated sludge not only improves the structure of the soil, but contains valuable phosphates and nitrates too.
So, there's a kind of microbe cycle. Some microbes are working to build up organic matter, whilst others break it down, releasing its ingredients for other organisms. It's microbes that even decompose us in the end. Some microbes are useful to us, but there are those that make us ill, and some can even kill us.
It was Louis Pasteur who, in the 19th century, first proved that microbes can cause disease. Later, the German scientist Robert Koch discovered the actual bacteria that caused diseases such as anthrax and tuberculosis. Joseph Lister applied the new knowledge about microbes and revolutionized surgery. He introduced carbolic sprays and other hygiene precautions during operations to prevent infections. Now, due to our increasing knowledge of microbes, many diseases have been conquered, yet some that we do get can still be prevented.
Take food poisoning, for instance. If we eat food that's been infected by disease-causing microbes, we may actually be eating the poisons that those microbes have produced. Or, once they're inside us, living microbes may start to multiply, producing sickness, fever, or severe diarrhea. Different microbes infect different foods. For instance, farm animals like this chicken may be infected by a bacterium called Salmonella.
This is what Salmonella looks like under a powerful electron microscope. It can infect humans and most farm animals, particularly pigs, cattle, turkeys, and chickens. Let's see what precautions are taken by the broiler industry to prevent Salmonella infecting chickens. Like all very young animals, chicks are not yet resistant to infection, so microbes must be kept away from the birds. The hatching trays must be washed and sterilized. All surfaces must be regularly scrubbed with disinfectant. A hatchery is like a hospital. The day-old chicks are moved to the broiler house where they will grow to marketing weight in under 8 weeks. Here it's more difficult to keep out infection. Salmonella is sometimes found in animal food, so all food is tested before giving it to the birds. Wild birds and animals may carry disease, and it's not easy to keep them out of the broiler house. Even the staff could bring in salmonella on their feet. That's why disinfectant buckets are used. Throughout their 8-week life in the broiler house, samples of litter containing the bird's excrement are taken to the laboratory to check for the presence of any infection. Samples are put into a special broth that encourages the growth of any microbes that may be present. The next day, using sterilized equipment, a single drop of this broth is put onto a dish containing a food substance on which salmonella will multiply further. All the labelled samples are put into an incubator at 37 degrees centigrade. By the next day, any bacteria in the samples will have multiplied and changed the colour of the plate, making identification simple.
-2686 negative.
In this test, harmless bacteria show up green, salmonella shows up red.
2460 positive, 2461 positive. 2803 negative, 2804 negative.
The positive results are tested further, and, if necessary, action is taken to prevent the infection from spreading. For the chicken, death is painless, but salmonella lives on. The dangers of contamination are far from over. Just one infected bird could contaminate this water tank. So not only is chlorine added to kill any microbes, but ice is continually dropped in to keep the water chilled. Microbes just aren't given a chance. Furthermore, water samples are taken regularly for laboratory analysis. With so many birds going through the plant, it is essential to detect any infection quickly before it gets a chance to spread. To do this, the laboratory tests 5,000 samples every month. Even the staff have regular medical examinations. Clean protective clothing and good hygiene are essential here. Finally, the birds are frozen and sent out to the shops. So the manufacturers have done what they can to control infection. Now it's our responsibility.
I'm not one that's easily put off my food. This chicken smells all right, and in any event, any salmonella that is present here will almost certainly be killed off during the cooking. So, let's get cooking.
This is a demonstration of how not to prepare food hygienically. Watch carefully. I'll make one more error that can lead to people getting food poisoning.
Right. 45 minutes, I think, should do it. We're all set. Here we are. Chicken ready. Well, it looks and sounds as if it's ready. Any bacteria that was in there to start with should be well and truly killed off by now. Any salmonella in there may well be still alive. Never mind, we can cope with that by popping it back into the oven and continuing the cooking for a little while longer. But will that cope with all the bacteria that may have been there to start with?
In a word, no. I'm sure you noticed that by licking my fingers, any harmful bacteria from the raw food would already be inside me. I should have washed my hands and dried them on a disposable paper towel, not a rag that could spread infection through the kitchen. And food must be in the oven long enough to heat right through. Food that's still partly frozen will look as if it's cooked long before the heat has reached the middle and killed any microbes that may be there.
We eat 300 million chickens every year, and most of them are like this, frozen. Now, some manufacturers put clear instructions on the back. This one, for instance, says, must be completely thawed before cooking. And a bit lower down, cook as soon as possible after thawing. But a bird this size will take 12 hours to thaw out completely at room temperature. A turkey, on the other hand, a much bigger bird, this one's just over 19 pounds, could take up to 36 hours to thaw out completely. Now, it doesn't say why you must thaw out carefully before you cook. But you know, don't you?